Right. So let's continue with part two of our study of solutions. You might recall that in the part one of the video, we covered different types of mixtures, such as homogeneous or heterogeneous mixtures, and discussed what their properties were. We then moved on to a very important idea, which is that molecules have a polarity to them. What that means simply is that the electrons are not evenly distributed throughout the molecule, and that they're concentrated in one part or another, and that leads to a polarity of charge. And that polarity has a lot of consequences, particularly in a solution discussion. Water is a very strongly polar molecule, and again, that has very big issues for us in solutions. We looked at the process of dissolving things, which again relies heavily upon the ideas of polarity of molecules. We then showed ourselves how to run a calculation for the concentration or molarity of a solution, and then ended with the notion of how do I carry out a dilution of an existing liquid. Now, and this is part two, we're going to take a look again at dilution. We're going to revisit it briefly, and then move into a really big area, which is the area of precipitation reactions. So let's take a look at precipitation and dilution. Here are some initial common terms. Again, this will probably be a review from part one for many of you. A stock solution is the one that is prepared and is in a concentrated form. We then have the phrase of a concentration is a large ratio of solute to solvent. And what that simply means is we have a large amount of solute, that powder, versus the amount of solvent. For example, a 5.0 molar NaCl solution is considered very concentrated. Something that is considered dilute is a relatively small ratio of solute compared to the solvent. For example, if you have a 0.01 molar solution of salt, it means that you have 0.01 moles in a full liter of for example, water. And clearly that level of salt is not very much, and we refer to it as a dilution. When we carry out a dilution, it's preparing a less concentrated solution from a more concentrated one. Now, what I'd like you to take a look at is that when you dilute a system, the actual amount of ions, the amount of powder, actually does not change. The number of moles, if you will, of powder present does not change. What does change is the volume that you find that many moles in. And the consequence is you get a greater spacing between the ions or molecules. And this greater spacing means there's fewer ions per given volume of liquid, and if this was orange juice, you would therefore experience it being less strong of a flavor per mouthful because there's less orange juice there and there's more water. So a dilution doesn't change the total amount of powder, it simply adds more solvent, which spreads them out more. And we refer to this as the before being initial and after being final. Now, to work with the equation, M1 MF VF, what you do is you simply have the molarity of the stock, the volume of the stock that you're going to take out, the molarity of the new solution, and the volume of the new solution. So let's take a look at an example. If you have 18.5 milliliters of 2.3 molar HCl, and it's added to 250 milliliters of water, what is the concentration of the new solution? Well, you have a initial molarity of 2.3, that's the stock HCl. It says you took out 18.5 milliliters of it, And the question is, what is the ending molarity going to be if you have 250 plus the 18.5 that you added? You punch the numbers in and you get a 0.16 molarity. Now notice, if you choose to, you can keep the volumes as milliliters. And by doing so, both volumes must then use those units. When you work with molarity, you must keep the molarity calculation in liters because the molarity value is based upon per liter. But that's not true here if you have volumes measured out in milliliters. Just take another example. Our stock solution is 4 molar. How would you make a 1 liter of a 0.75? We would punch the numbers in. Our initial molarity is 4. The volume you're going to use, I don't know that number yet. But I do know that in the end, I want the molarity to be a 0.75 molar, and I want it to be a total of 1 liter. Notice in this case, the choice being made is to keep the volumes in a liter value. So when you do so, the volume of the stock you want to work with is 0.19 liters. If you now want to measure it out as milliliters, you would simply have to do the unit conversion. And of course, that's a 1 molar solution. But that's the 32 molar solution. And that is arguably actually kind of gross. But there you go. So, those are your basic ideas behind the dilution process of a solution. Now let's take on a new idea. This is a totally new idea. It's the notion of a precipitate reaction. Now you've seen in class in demonstration form types of chemical reactions already. One type was when we had the flaming bubbles. We took the natural gas and we put a match to it and it burst into flames. That, of course, that's a combustion reaction. That's one type of reaction. Another kind of reaction, totally different from it, but one that is very, very common, is called a precipitate reaction. And we need to understand these. What exactly goes on in a precipitate reactions? First of all, you start with aqueous solution. Now, what that means is precipitate reactions typically do not involve solid to solid. They do not typically involve gas to gas. We think of precipitate reactions as aqueous solutions. So what you see here is you have a medicine dropper, and that's on top, and it has a yellow solution in it, yellow gold. Now if you look off to the side, this is a beautiful diagram. I love this setup. Thank you, Google. But if you look off to the left, what actually is in that solution? Well, it's water. How do you know? It's aqueous. So you know it's dissolved in water. Well, what's dissolved in there? There are K plus ions, potassium ions, and there's also Cr2O7 minus, and those are dichromate ions. And so those two ions fill the water area, and that gives it the color. Now the first argument is, well, why doesn't the K plus and the Cr2O minus, why don't they hook up? Why don't they combine? Opposites attract. Well, the answer is they do attract, but the strength of that attraction is not good enough to overcome the attraction that the polar water molecule has for them. So you see, water is attracted to the K plus because it's polar. And water is attracted to the Cr2O7 minus 2 ion. And it pulls it so strongly to itself that the two ions themselves cannot hold together. Therefore, they remain soluble. They remain dissolved. And therefore, we call that an aqueous solution. Now, you work down below and you say, wait, K2Cr2O7 aqueous. It looks like, when you write it out that way, that it's a molecule. But it's not. When you see the letters AQ, aqueous, what you're being told is those exist as ions in the water. It's aqueous. Now look below. If you take a look at the beaker, there's this clear liquid. Looks like water. Well, in fact, a lot of it is water, but dissolved in that water is silver ions, Ag+, and nitrate ions, NO3-. And by the same argument that we just had before, Ag, NO3, they do attract each other. They are opposites, but the attraction is not particularly strong. For whatever reason, the orientation of the molecule is not very good. The overall arrangement of the electrons is not favorable, but for whatever reason, those two ions are not successful in holding on to each other when it's surrounded by this polar water. The result is they remain aqueous, and you see below again the AgNO3 aqueous denotes that. But then something pretty slick happens. When you put the yellow gold liquid, shown as a drop, and mix it with what looks like the clear liquid, which is the silver nitrate, suddenly this blobby yellow lava lamp thing, suddenly it starts to form. What is that red stuff? It's a solid. Now, true, it's made up of solid of very, very small granulars, so it's not a true blob. You can't reach in with your hand and pick that whole thing up like a solid object. But in fact, what has happened is a whole bunch of these reddish granular solids have formed. Now, how did that happen? Well, it turns out that when you mix those two solutions, the potassium dichromate and the silver nitrate, when you mix those, two ions come in contact with each other that weren't in contact before. Notice on the right, what happens is the silver, Ag, is attracted, Ag plus I should note, is attracted to the chromate, -2. Now, for a variety of actually complicated reasons, that silver plus Cr2O minus or 7 minus, that attraction is really strong. It's powerful. So powerful, it overcomes the effect of the water, and they bind tightly together to make a solid. And a whole bunch of those glom together to make these red granular solids. Now, those red granular solids, they're called a precipitate. And again, they're a solid. What about the potassium, K+? What about the NO3-? Aren't they also attracted? They are. But once again, for a variety of reasons, the strength of that attraction is not good enough to overcome, and therefore they remain ions dissolved in the aqueous solution while the silver dichromate forms a solid precipitate. Now, if you look down at the very, very bottom there, we give you the actual reaction for this. Silver nitrate aqueous, potassium dichromate aqueous. Arrow means a reaction happens. You get silver dichromate solid. There's the precipitate. And there you get the potassium nitrate still existing as an aqueous solution. So I've kind of walked you through what I consider to be just a fantastic, elegant slide to show you the basic principles of precipitate reactions. We're going to now look through several examples of this again. I'll talk it through again. We'll look at some charts. But what we're going to be talking about in detail is what you just saw here. Now, besides precipitate reactions, there are other kinds of reactions that can take place in a solution. First one, of course, is the precipitate. And this is another precipitate reaction, not the one you just saw, but this one does involve silver. But that's a precipitate reaction. You know so because look after that reaction arrow, AgCl2, AgCl, that's a solid. But what else can happen? You can have acid-base reactions. These are also referred to as neutralization reactions. And actually, later on in this unit, within a few days that you watch this, we'll be studying these acid-base reactions because they are an important kind of reaction that takes place. And the final type are called oxidation-reduction reactions. These are even more complex, more sophisticated. We'll look at these at the very end of this course, but these are your three basic types of reactions that happens with material that is in solution. So let's explore more precipitate reactions. The precipitate is called insoluble. That's an important word for you to know. Insoluble means it's not soluble. That is to say, it won't dissolve. And it separates itself from the solution. So here we see the use of the aqueous for the lead nitrate, aqueous for the sodium iodide, but then again right there, that's the precipitate. How do I know it's the precipitate? Because it forms a solid. Which raises an interesting question, which is it possible for a solutions reaction to form two precipitates in which both sides actually form solids? The answer is it does. It's possible. Rare, those are called double precipitates. And it can happen. There's nothing chemically against it. It's just rare to find those combinations. Now here's your precipitation of lead iodine. We're going to look at precipitation now at an atomic or molecular level. Now what you notice in this box is you have a bunch of red and gray molecules. Those are water. Always remember, water's polar. One side where the hydrogens are is plus, one side is negative. And what you see is a bunch of ions inside. There's K, green, potassium. There's the I, purple. That's the iodide. You have the Pb, that's the gold or yellow, and that's going to be the lead. And you have the nitrate, NO3 minus. Now, all of those ions are held separate from each other. Why? Because the water, which loves to have these ions around them, why not? They are polar. These ions are charged. It's a very good situation. And so the water kind of envelops them and prevents a lot of good attraction because there's a separation, a blockage due to these water molecules. But what of course happens is, in the case of lead iodine, the attraction between the lead and the iodine is stronger. The attraction pulls the lead and iodine together. It literally squeezes the water out of the way, and you see this formation of a solid, in this case lead iodide. And you can notice that the potassium and the nitrate still remains in solution simply because they cannot attract each other hard enough to get together because the water separates them. If you'd give a summary reaction, what's referred to as the net ionic reaction. The net ionic is Pb plus 2 plus a 2i come together to make the PbI2 solid or precipitate. You actually do not include the other ions because in fact they don't participate in the formation of the solid. The formation of the solid, that is the reaction. And there you see it here. It turns a wonderful, wonderful snot-looking yellow. Most elegant. So what exactly is examples of what's insoluble? Well, cadmium sulfide, lead sulfide, nickel hydroxide, aluminum. These are solids. When you put those ions in solution, they're going to form a solid. How do I know? Is it possible to predict? Absolutely. You have a chart. In this chart, you're going to be asked to use a fair amount in the next few days and on exams that take place. So let's make sure you know how to work with this chart. And I should give you a heads up that you will find this chart on the back of the polyatomic chart that you have as a resource. And yes, of course, you'll use this chart during all exams. You have it in front of you. Nothing to memorize, but you must understand it. Now look on top, it says under A, soluble compounds. Now what that means is everything in gold, nitrates, sodium, potassium, ammonium, chloride, bromide, everything in gold, if it's there, it's soluble. What does that mean? It means it's always going to be dissolved. Anything that has nitrate in it, NO3 minus, it's going to be a soluble. It's not going to form a solid. If you have any molecule that has Na, K, NH4, if that molecule has that, I should say if that compound has that, it's going to dissolve. It will not form a solid. And now take a look here. Chlorine, bromine, iodine, any compound that has that stuff in it is going to be soluble. It's going to remain dissolved. But if chlorine or bromine or iodine is attached or held to silver, mercury, which is Hg, Pb, which is lead, then it does precipitate out. So silver chloride, Ag plus, Cl minus, that's going to form a precipitate. Pb plus 2I2, that's the lead iodide. That is going to form a solid because that's an exception. Skip down, SO4 minus 2, that's going to always dissolve. It's soluble except when SO4 minus 2 is in fact forming a compound with BaPbCa. So you can read this chart and predict in advance what in fact should form a precipitate and what should not. Now let's get down to part B. Under part B, those items that are in kind of the greenish, bluish gray, those are insoluble. So for example, sulfates, carbonates, phosphates, all of those compounds are always insoluble, meaning they will form a precipitate. OH minus, that's always going to form a solid, except when it's NaKCa. Then it's going to be soluble. So that's the exception. So you want to be able to work with this chart and master it in order to make predictions from it. Now, when you write down precipitate reactions, there are some general rules you have to write down. There's your precipitate. We saw this before. This is known as the molecular equation. What does that mean? Is you've listed the molecules or compounds that are involved, and you list them before they actually get dissolved. So these exist initially in the powder form. They're referred to as the molecular equations. Now you know they're going to dissociate, you know they're going to dissolve because the aqueous denotes that. Now this is referred to as the ionic equation. The ionic lists each of these ions as they would appear in a solution. And you'll notice it has to be balanced. So you have 2 NO3 minuses. You have 2 NAs. So you must balance both sides of the equation like you normally would. So this is your ionic equation. Now notice, when you look at this, the nitrates appear on both sides, and the sodiums appear on both sides. And your argument would be, well, of course, they didn't form a solid. They remain as separate ions. So they were ions to begin with. There are ions on the end, so they appear on both sides. That's correct. So you can actually cancel those out. And that will give you just what we saw before. This is known as the net ionic equation, where you list only the ions and the results that are participating in the precipitate reaction. And this is the precipitate reaction because this is where the solid forms. Now, it is important you realize you're going to be asked to draw molecular equations, to draw net ionic equations. So these formats you need to be familiar with. Now, what about the Na plus and the NO3s? They never got involved. They're referred to as spectator ions, meaning they do not get involved in the reaction. They simply spectate and watch. So, if you're told 581 milliliters of a 0.342 molar barium nitrate mixed with excess potassium sulfate, producing this precipitate, write the balanced molecular ionic, net ionic for this reaction. So let's take a look how you'd write this out. So you got barium nitrate reacting with potassium sulfate to produce the barium sulfate and potassium nitrate. Whoops, my bad. Now the mistake actually shows up here. We never identified what is aqueous and what is the solid precipitate. And you would normally need to. This one did not. But that is the molecular equation. This, of course, is going to be the complete ionic equation, where we in fact list each of the separate ions that would appear, and this is the net ionic equation, and those are your spectators. And that's you.